I will try to be brief, but not that brief. I'm actually lying to you. I've been given 20 minutes. I don't think I can make it in 20 minutes, but I'll try. What I wanted to do here is just a little slight brush on top of the Yemoja system, just so you have a general understanding of what some of you will be playing with very shortly. But let me start, actually, you know, everyone knows that the Yemoja system is meant for HPC, but do we all know what high-performance computing is? So let me just give you a brief overview on HPC before we actually talk about the system itself. So when we all talk about high-performance computing, the first thing that comes to our minds is are actually those pretty big, pretty large machines, you know, those old mainframes, that fit inside a room, make a lot of noise, and actually do have a lot of compute power. But is HPC actually that? Or when we talk about HPC, do we actually mean these machines, these large systems? When we come to HPC, actually, we're all talking about resolving the obstacles to disruptive innovations. So HPC per se is not the important bit. The important bit is we want to solve these obstacles, and we're using HPC for it, regardless of what HPC actually is, okay? When we talk about disruptive innovations, we mean very complex challenges such as weather forecast, stock market pricing, challenges of very high investment such as rocket modeling, oil exploration, very time-demanding challenges such as galactical movements. You know, the people from astrophysics are extremely interested in knowing when Andromeda is colliding with the Milky Way. Effects of medications, this is extremely important for future medical developments, and especially ethically bound challenges such as nuclear tests and stem cell research. When we come to these disciplines, there is a lot of debate whether we should do these experiments in reality or not. I mean, bombarding around is not the best approach ever, right? So this all becomes feasible when we start endeavoring into computational simulation. That is running an actual simulation, but not in reality. Instead, we use the computer to play around with data collected from the real world using algorithms or using skills that can mimic how the real world actually is, and not doing it in reality, but getting to results that would mimic how reality is. This is essentially what HPC is. It's not a machine, but instead, it's hardware, software, techniques, tools, methodologies, algorithms, libraries, all of this that permits calculation and heavy processing, often of large amounts of data, used in computational simulations for scientific and engineering purposes. So going back to the previous initial question, what is HPC? HPC is not a large machine. HPC instead is this complex, you know, ecosystem of hardware, software, techniques, algorithms, tools, a lot of which you build, a lot of which we build, a lot of which we get companies and open source initiatives building, all of this to support computational simulations for engineering and scientific purposes. How do we actually use HPC? So we take a scientific model and we map it very well to software and map the software very well to hardware so that we can extract performance back. The whole idea is that the model can be very well mapped to hardware so that the full hardware potential and the full software potential can be exploited to its full power, okay, to its full extent. This means that HPC, as we've just defined, it defines the upper limit to computational capacity and capability. What we actually play with in terms of HPC, in order to resolve these great challenges, these disruptive innovations, we really need a huge amount of compute power, a huge amount of storage, and not only huge amount, but very efficient storage. It means that we are playing with the very upper limit, meaning that HPC is the forefront in terms of efficient storage and computational power. We're really breaching, you know, to the boundary, to the upper boundary of compute power and storage in order to resolve these grand challenges we are facing with. All right? Just to give you, again, to finalize this HPC introduction, I just wanted to talk a little bit about the HPC market. So we're talking about, in terms of HPC, at least 350 prominent players among integrators, manufacturers, developers of HPC technology, a number of research groups around the world playing within industry, trying to resolve these grand challenges. And just a little figure coming from Intel, we have about over 30 million processors sold annually, only in terms of HPC, only for HPC purposes. The largest trade fair, which is called Supercomputing, happens every single year and welcomes over 11,000 attendees every year. So we're not talking about a small community. What we're all seeing here is a very huge effort to solve grand challenges from researchers and people within industry all around the world, and about $20 billion in global market deals as of 2015, with an estimated by IDC compound annual growth rate of 8.5% over the next 5 years, reaching $31.5 billion by 2019. This is not a small market, it's actually extremely large. And this all happens, and it is all because we have a huge number of challenges to resolve, and those won't come for free. There's no free lunch. Okay? Now we actually go into the actual Yemoja system. I wanted to give just this brief perspective into HPC before we talk about it. So the Yemoja system is our use case for the I'm using it as a use case for the III initiative. And this all happened because of the problems all of you have. Seismic imaging. We have been introduced to this problem by our friends at PG, who came to us with the challenge saying, but look, we have a huge challenge here. We would like to especially tackle the pre-salt, but it's under this huge layer of salt. It distorts or waves, and we produce a huge amount of data, petabytes of data in just a few shots. How can we actually accomplish that? It takes a huge amount of compute to use the fanciest algorithms to try and image the underground. So, I mean, this is, all of you know, the latest algorithms such as FWI Elastic use a huge amount of memory and disk space. So it's not a simple problem that we can tackle just by using common computers for running this type of computational simulation. So within Brazil, ourselves, we are SENAI. SENAI stands for the Service National Apprenticeship Industrial at the Federations of Industries in the state of Bahia. We partnered with PG with the help of ANP and a number of local partners to come up with the Supercomputing Center for Industrial Innovation. Within Brazil, we bring to all of you the Yemoja system to help sort out this challenge. And we're supporting especially the International Inversion Initiative in the challenge of bringing the latest seismic inversion algorithms to the HPC space to solve the grand challenge of imaging the underground. Okay? The point is that we needed these tools to allow us to solve the issue of seismic imaging, but we needed to solve this issue in due time. I mean, if we use a common computer, we can solve this issue in a few centuries, but it won't help us. We want to solve it now. That is why we launched in the end of May the Yemoja system, which, just a little note, by the way, Yemoja is the Afro-Brazilian deity. Actually, Yemoja, as we call it in Portuguese, is the African-Brazilian deity that looks after the oceans. She is the goddess of the oceans, and also the mother of all other gods in the Umbanda religion, African-Brazilian religion. Okay, just a few photos of the system. As many of you haven't seen it, This is the front perspective of the system. These racks are all compute racks. These racks in the end are controller racks, storage racks, and login racks. Another perspective from the opposite direction. So storage, control, and login racks, compute racks. We have more racks in the back, but you cannot see in this perspective. What we have in the system, actually, but even beforehand, it's important to mention that this system can reach 405 teraflops of theoretical, of sustained performance, which means 405 trillion operations using real numbers, okay? And it is the #1 most powerful system in operation in Latin America. Also the number 1 most powerful system for oil and gas research in Latin America and the Southern Hemisphere, so including Australia, New Zealand, and the like. Yeah, which is important, you know, we're competing with very high powerful ones. Number 167, the most powerful one globally in operation at the moment. And only 5 other HPC systems exist in Latin America. If we compare it to the next one, HPC system in operation, it is almost twice as fast, all right? And as I mentioned to you in the very beginning, it is very strict access control to this system. That's why I cannot give you a demo right now. Looking from a comparison perspective, what we have inside the HPC system is in terms of CPUs. Comparing to a commodity PC that has only 1 CPU, we have 1,716 CPUs. A total of 132,000 gigabytes compared to 4 to 8 gigabytes in your common computer. CPU cores of 17,200 compared to 4, you know, your quad-core computer in your home, 4 compute cores. 2 million gigabytes of storage compared to, say, you have a 600 gigabytes or 1 terabyte of storage. That's a huge amount of storage. And a peak performance of 405,000 gigaflops, whereas your computer at home can reach only about 10 gigaflops, which means this machine is akin to at least 40,000 commodity PCs, okay? For some of you who are very technical, let me give you a brief understanding of the system and why we ourselves with PG and the remaining partners reached this specific architecture, which is an i6 with 860 compute nodes. The point is, we needed all these compute nodes. See, we have 2 Intel processors per node with 10 core, and each node with either 128 or 256 gigabyte RAM, in a total of 17,200 compute cores. We needed all of this because we do need a lot of compute. And we not only need a lot of compute, we need a lot of RAM per node in order to fit all our seismic data within the RAM and avoid going back and forth between RAM and CPU, okay? This is why we need this much RAM. It is a huge amount of RAM. Just for you to have an idea, a new HPC system that is about to launch now in early October in the National Lab here in Brazil, the National Computational Science Lab in Brazil, has only 64 gigabyte RAM per compute node, which is considered by them to be a huge amount of RAM per compute node. We actually have a lot more. We have over 2 petabyte integrated storage. This is all meant to host your seismic data. And a lot of interconnect based on fiber optics for fast communication between the compute nodes. We do actually need that to run the simulations as fast as possible because all of the seismic data for simulation will be split among the compute nodes for parallel execution. Likewise, for I/O rate, we cannot fit all the data within RAM. We have to keep a lot of it in disk, and I/O rate as fast as possible will allow us to diminish the time for execution. Okay? Brief perspective, not on the machine, but instead on the backyard, on the behind the curtains of the system, just so you have an idea of how complex setting all of this up has been to all of us. The HPC data center is within these dotted lines here in the corner, which hosts all these CDUs, which are heat exchangers for the water cooling for the system, and the cross, which are the precision air conditioning systems to keep the data center cooled down. Okay, this whole picture here is the cooling system that feeds the HPC machine. Here on the bottom, we have the chillers, which are a set of pumps with redundancy, and a water tank in case the chiller fails or needs to be maintained. Likewise, here in this other cycle, the red cycle, we have dry coolers, which are meant to cool down the water that flows within this red cycle whenever the external temperature, which is seen here, is below about 26, 27. And these pumps here are all redundant. So we have the blue cycle with very colder water that is cooled down by the chiller and exchanged heat with this other cycle, red water, which is less cool down, that is cooled down whenever possible by the dry cooler. And these all exchange heat with the CDUs, which are the heat exchangers for passing water within the system. So the system is all cooled down by water, which means that this system is extremely sensitive to temperature fluctuations, extremely sensitive to, say, humidity within the room. And keeping all of this alive has been extremely complex to us. It's a huge amount of work, okay? And not only in terms of keeping the room safe, but also in terms of making sure that all support is given to all of you whenever possible. So we all know that computational systems are made of hardware, software, and peopleware that need to provide support to hardware and software. In our case, here in the middle, we have a very important bit, which is the system environment, operating systems, compilers, and we need people to take care of all of that. I mean, both in terms of actual hardware, coolers, chillers, dry coolers, pumps. In terms of hardware, the actual system, the compute system, the Yemoja machine. In terms of system environment, OS compilers. In terms of software, running the models and helping you bring the models to the system and porting and making the models as efficient as possible using the Yemoja machine. And all of this, we're very keen to support you with. Okay? But then, if you're ready and you wish access, how do you do? Actually, first of all, come talk to me. I will be happy to understand your situation and walk you through should it be necessary. And when you're granted access, all the access, differently from most systems which are accessed by SSH, in our case, you're going to be given an actual desktop, virtual desktop for you to play with. This is, again, because of security. If you access by SSH, you will allow all the data to be transferred back and forth from the HPC system to your computer. Here, it's only send a keyboard and mouse and get back visuals, okay? But you can also do the same as you can do often with SSH. You go to terminal, you'll be granted a terminal, and you play around as usual, all right? Brief overview to the software environment. Operating system Red Hat 6.5, we have compilers all you can need, especially Intel ones. All MPI libraries that you can think of, including the Intel MPI, MPH, MVAPH, Intel OpenMPI. All sorts of interpreters such as Python, especially MATLAB, extremely important for those who play with computational simulations at high level. Libraries, FFT, HDF5, a lot of productivity tools, and our batch scheduler is Slurm. Okay? And this is all within the Supercomputing Center for Industrial Innovation, which is comprised of especially an area, say a department for oil and gas modeling, which is supporting the International Inversion Initiative. But we also have another department for modeling for Brazilian industries. And in this case, we're about to procure a second HPC system, extremely smaller, instead 50 to 100 teraflop theoretical performance, to support the Brazilian industry and educate HPC developers to support all sorts of modeling, including seismic imaging, to support the needs for Brazilian industry, especially supercomputing assisted engineering for the purposes of prototyping, more simplistic simulations, product design, especially in our case in Bahia, which has a very fast industry in also automobile and oil and gas, and assistance to startups and SMEs to push industry forward. Just to finish, we are hiring, so we're looking for especially students, but not necessarily students, undergrads, masters, PhDs, and postdocs to support our HPC in our research in high performance computing, and operating the #1 HPC system for oil and gas in R&D in Latin America to develop these and optimize these libraries and codes for seismic imaging especially, and work in actual real projects with business impact in the industry. So with this, I thank you very much, and I'm open for questions.